name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is another proof in differential calculus. This proof is about differentiability implying continuity. That's the shorthand way of saying the following theorem. If f is differentiable at a point A, then it's got to be continuous at that very same point. This is not to be confused with the converse. The converse of this is not true. So I wrote it here as a warning. Continuity at A does not imply differentiability at A. So as a simple example, you could take the shifted absolute value function, or any absolute value function, honestly, is a great example, but I'm just shifting it so you can kind of see. And we'll say at A, that's x equals A, you could easily see that this function is continuous because to draw it, I would not actually have to lift my pen. However, this is definitely not differentiable at A. And this brings into play what our prerequisite knowledge has to be for this proof. The first item for our prerequisite knowledge will be that you have to be extremely familiar with the limit definition of a derivative. There are actually two popular forms of the limit definition of a derivative. The first is that f prime evaluated at A is equal to the limit as h approaches 0 of f of A plus h minus f of A all over h. This is actually my favorite. I like that limit definition a little bit better than the other limit definition, just because this one is, in my opinion, easier to use. However, for this proof, we're going to use the second definition of a limit, or of a derivative at A, which honestly is the one that I think is most easily understood from an algebra standpoint. It's difference in y values over difference in x values as the x values approach each other. So that's the limit form of a derivative. And that's, remember, a derivative is just a limit. So that's the technical definition of a derivative. The other piece of information that we'll have to have, our prerequisite knowledge base, is the idea of continuity. Specifically, that a function is continuous at a point A if its limit as x approaches A is actually equal to the function value evaluated at A. So not only do the left and right hand limits exist and meet up, but they also actually equal what the function is at A. That's what continuity is. We're going to use both of these pieces of knowledge in this proof. So let's go ahead and start the proof. I'm going to hop back to the original page here. The theorem says we have to let f be differentiable at A, and we want to show that it's continuous at A. So let's go ahead and suppose that it's differentiable at A, which completely implies the following: that the limit as x approaches A of f of x minus f of A over x minus A is actually equal to f prime at A. So we happen to know that this derivative exists. Maybe I should even write that down below. This exists. So then f prime at A, which equals that, must exist. Now, as often things go in proofs, we need to kind of do a little bit of scratch work to kind of give ourselves a roadmap. So my roadmap is I want to show that f must be continuous then at A. So we want to show that f is continuous at A. This is all my scratch work. I'm very short-handed with my scratch work. To be continuous at A, that means that the limit as x approaches A of f of x, we would love that to actually be f of A. That would show continuity at A. So that's where we want to end up. So let's go ahead and write therefore. Just kind of move on here. And we'll start with the limit as x approaches A of f of x. Now remember, I want that to turn into f of A. So I'm going to have to start manipulating this so that it will turn into f of A. And all I know here is that the limit as x approaches A of f of x minus f of A over x minus A exists. So that's kind of important. I want to get f of x minus f of A into my statement. So why don't we say this is equal to the limit as x approaches a, and I'm going to force that statement of f of x minus f of a in here. So I'm going to say that's f of x minus f of a plus f of a. Now that you can probably agree should be true, right? All I did was subtract and add the same number. So I've done essentially nothing. This bit right here, all that is 0. So I've done nothing. Now we're going to split that limit. And something that I tell all my calculus students, and maybe I don't want to start splitting it there, something I try to tell all my calculus students is that you cannot split a limit unless each of the splits exist. So in this case, we're going to cross our fingers and hope that this is actually very true. I'm going to split this into the limit as x approaches a of f of x minus f of a plus the limit as x approaches a of f of a. Now, let me tell you why we can do the split, at least the second part of the split. Our supposition that f is differentiable at a implies that f exists at a. Okay? So, because the derivative at a exists, then f itself at a must exist. The derivative of a function always has the same domain or a little bit less of the domain than the original function. So if the derivative contains the point a in its domain, then the original function must contain the point a in its domain as well. So this second limit is perfectly fine. We're still not sure about that first limit, but let's see if we can mangle it a little bit so that we can convince ourselves that the limit exists. The limit as x approaches a of, and now I'm going to do a big trick here. I'm going to say, actually I don't need to do the curly cues. I'm going to say that this is f of x minus f of a. Now remember, my goal is to use this limit right here. So what I'm going to do is put this over x minus a. And then I'm going to say, you know what, I could do that because I'm going to put in the numerator, I guess I will use curly cues here, I'll put in the numerator an x minus a up there as well. So if you look at this, I've actually done nothing but multiplied the interior of that limit by 1. So nothing has actually happened. By the way, the limit as x approaches a of f of a, that's f of a. Now we're getting somewhere, because remember, I can only split those limits if they exist, and I'm crossing my fingers that I didn't make a mistake by splitting that limit. But if you take a look at this, we did say something about the following. I'm going to do this another split here. I'm going to split this into f of x minus f of a all over x minus a. That's that first limit. I shouldn't use that circle-y bracket. I'll use a brace here. And then times, so I'm splitting this limit as well. So I've done a double split, but again, in the end, I'm going to go back through and make sure that I could have done that. Okay? So what you're looking at right now is that not only did I split this original limit, the one right here, I not only split that into the sum of two different limits, but then I split this other limit right here that I kind of mangled with into the product of two different limits down below. And I'm telling you right now that that actually could happen because we know that this first limit exists. It exists by our supposition. So let me write that in, supposition, and I'll show you. That limit exists by our supposition because we supposed that f is differentiable at a. In other words, that f prime at a, which is equal to the limit as x approaches a of f of x minus f of a over x minus a. So this picture right here, that guy right there is the same thing as this guy right here. We have stated that that exists. So we know that split exists. Obviously, the limit as x approaches a of x minus a, that also exists. I mean, that's an obvious one. So because this split exists, this limit we were perfectly okay with splitting that limit, and we were perfectly okay with splitting those limits. So this just, I get down to a point, I split, crossing my fingers, hoping that the split was a fair thing to do. And when I get down to the bottom there, I find out that, oh yeah, that split is perfectly fine because the first part of the split is okay. Let me highlight that again. The first part of the split at the very bottom is totally fine. We've said that exists. The second part of the split, well, that's okay as well because I know that that is going to turn out to be 0, right? The limit as x approaches a of x minus a, well, that's just going to be a minus a, or 0. So this is going to equal some number, actually not just some number, honestly it'll equal f prime at a. So the first split turns into f prime at a times the second split turns into 0 plus f of a. So the first term is just 0, so this disappears and we get f of a. So hold on, let's see what we just did. We just proved that this is a continuous function. Why? Because the limit as x approaches a of f of x is equal to, through a chain of equalities, f of a. Let me write that down. Thus, the limit as x approaches a of f of x must equal f of a. Hence, I don't have room down below, so I'll just write it right here. Hence, f is continuous just at a. All right. And literally, that is all there is to that proof. It seems like a lot, but actually the logic behind it's pretty good. So rewatch this if you need to. It'll take a little bit to convince yourself. Probably the hardest part of a proof like this is being okay with the fact that we can split these limits. Remember, you cannot split a limit if the split results in something that doesn't exist or is not finite. You have to split into numbers that are finite. Luckily, all these splits did that.